Hi everyone, my name is Gabriel Huang and I'll be presenting my Google internship project on multimodal pretraining for dance video captioning. This is joint work with Bo, Chenhai, Clara, and Radu. So let's start with the motivation first. We know that in the past years, video consumption has been growing a lot. In fact, the average person is forecasted to watch 100 minutes of videos per day in 2021. And actually, instructional videos are a big part of it. People go to YouTube for how-tos and tutorials. But videos are inherently hard to skim through, and I find myself repeatedly clicking on the timeline in order to scroll through a tutorial. Users can benefit from metadata such as timeline annotations. Search engines such as Google have started linking to key moments in videos. So for instance, if you look for sourdough starter on Google search on mobile, you'll see the videos, but also under them an annotated timeline. So each of the steps will appear here and with a short caption that describes what the step consists in. The question is, can we generate those timeline annotations automatically? We can reduce timeline annotation generation into two tasks: segmentation, splitting the video into different steps, and video captioning, generating the labels for each of the steps. In this work, we focus exclusively on dense video captioning. We assume that the video segments are already given, either hand annotated or by another algorithm. The first step is to transform the audio of the videos into text. So this will result in the narrated instructions because we're looking at instructional videos. We use YouTube API's speech recognition engine. So the inputs to our algorithm will be the video, either in 2D or 3D features, and the ASR, automated speech recognition. The expected output is the caption, so the step summary. We considered two tasks: text-only video captioning, going from ASR to caption, and multimodal video captioning, where we add also the video feature as input. The summary of contributions in our paper is as follows. First, we propose video timeline tags, or ViTT, a new dense video captioning dataset. It features a wide range of activities and is more challenging than YouCook2. The second contribution is multimodal pretraining for dense video captioning. So we explore several pre-training and fine-tuning strategies. We get state-of-the-art results on YouCook2, and we get good baseline scores for our new dataset, ViTT. Let's talk more about the datasets now. These are the 6 datasets that we consider in this paper: 4 datasets for pre-training and 2 datasets for fine-tuning. So let's look at the fine-tuning datasets first. So those fine-tuning datasets are parallel data, and they contain ASR, video, and captions. So we'll be looking at YouCook2, which is standard, and ViTT, our new dataset. And we'll use them both for fine-tuning and evaluation. So let's look at YouCook2 first. As you can see, all the videos are about cooking, and the captions are recipe steps. The problem for our application is that the captions are very lengthy. On average, are almost 9 words. So this is not very good for timeline tagging, where we want short titles for each of the steps. One problem with this dataset also is that it requires limited generalization. Videos about the same recipes are split between training and testing. So there are no new recipes in the test split. So it requires limited generalization. Now let's look at our new dataset, video timeline tags. As you can see, it features many activities: makeup, still some cooking, home repairs, arts and crafts. There's also more things such as car mechanics. The captions are very concise, about 3 words on average, which is good for timeline tagging, and it requires stronger generalization. We didn't explicitly enforce that the same activities should appear in the training and in the testing set. Because parallel data, such as the ones we just saw, YouCook2 and ViTT, are expensive to acquire, we also consider unpaired datasets for pre-training. So basically 2 types of unsupervised datasets. The first type is similar to the input, and they contain ASR and video. So we look at YouTube 8 million and how-to 100 million. The second style of pre-training dataset is similar to the output, and there are caption style datasets. So we look at recipe 1 million. So it looks like recipe steps. And we also look at WikiHow. We take the first part, the header of each step, and we take those as tutorial steps. Architecture. Our transformer-based architecture consists of separate encoders for the ASR and video. This is the encoder with the ASR part on the left and the video part on the right. We have cross-model attention between the two, so they can attend to each other. And then we have a text-only decoder to predict the captions. So the decoder is here, and it can attend both to the text and video features. Because this diagram is fairly complicated, we'll be simplifying it throughout the rest of the presentation in the form of a data flow. So here we have represented the data flow for dense video captioning. We feed ASR, so the narrated instructions, and the video features as input, and we'll be expecting captions as output. Pre-training and fine-tuning. We explore several combinations of pre-training and fine-tuning objectives. So you can basically group them into three categories. We have the text-only pre-training objectives, multimodal pre-training objectives, and then the fine-tuning objectives. So let's start with the pre-training objectives. But before that, I need to introduce a pre-training strategy commonly used in sequence-to-sequence problems called mass pre-training. So this means masked sequence-to-sequence pre-training, and it's been successfully applied to sequence-to-sequence problems such as unsupervised machine translation and summarization tasks. So the way it works is very simple. You start by feeding a sequence to the encoder, but you mask a random subsequence. Then the decoder has to predict the hidden subsequence, and it is trained using teacher forcing. So you can see it's just been shifted to the right here in the input. The advantage of using mass pre-training is that it jointly pre-trains the encoder and decoder. And so it's going to learn this attention module. In comparison, if we were to use approaches such as BERT or language models, then we could only pre-train the encoder or decoder separately. So we have no guarantee that it would also learn the attention module. So we'll be using this mass pre-training strategy on caption-like datasets, recipe 1 million WikiHow, and also on the ASR-like datasets, so YouTube 8 million and how-to 100 million. Now, mass pre-training is text-only, so the encoder might not learn how to use the video. So we do the obvious. We extend mass to the multimodal setting by allowing the encoder to also condition on the video. So here we added the video. But we have no guarantee that the encoder will attend to the video features, which is why we also investigate randomly dropping the ASR features to force the encoder and decoder to attend to the video part. We also investigate another type of pre-training objective, which is that we'll make the encoder predict for two randomly sampled ASR and video segments from the same video if the ASR and video happen at the same time, so if they are aligned or not, and if they do not occur at the same time, which one occurs first. So it's two binary prediction problems. The encoder has no other way to solve it than to look at the ASR and the video. So this seems like a good approach for learning attention between the two. So we'll see in the results if it helps. Now let's look at the fine-tuning objectives. Our end task is to solve dense video captioning. So the input will be ASR and video, and the output will be the captions. So we will be training our model on YouCook2 or ViTT using this objective. We also investigate complementing this forward objective with a reverse fine-tuning. So we'll be feeding the expected output, the captions, as input, and trying to make the model hallucinate the expected input. And we'll see that in some cases it can help. We also have variants where we feed the video here. So let's look at some example predictions, and then we'll talk about the numbers. So here are some predictions on YouCook2. So the ground truth here, for instance, would be place wings on the baking sheet and cook flipping. Without pre-training, the model predicts bake the pizza in the oven. So this is incorrect because it's actually about chicken wings, not pizzas. So the model just hallucinated it, probably because the speaker talked about an oven. But with the pre-training, we get the correct prediction: cook the wings on the grill. In general, you can see that the trend is that with pre-training, we always get better results than without pre-training. Now here are some results on ViTT, which is much more challenging. You can see here again, we have the trend that using mass pre-training is better than no pre-training. Here's an example, highlighting brow bone. The model without pre-training predicted applying eyeshadow, which is kind of close, but it's not correct. With pre-training, we predicted brushing out the brows, which is much more accurate. Here are also some examples of bad predictions. Ground truth is starting with unlocking bars, so it's about bars on the roof of a car. Without pre-training, we predict opening the box. With pre-training, we predict pulling the car on. So both of those predictions are bad, or they're not specific enough. And one of the reasons is just that our data set is very challenging. This activity did not appear a lot in the training set. So let's look at the scores and the ablation study now to better understand what the model is doing. So first, those are results on YouCook2. Here are methods from the literature. Univelm is concurrent work. So the first observation that we have is that we get the best score using multimodal pretraining here in red. So get about 39 rule score. But we also get very good scores using just text pretraining. So just using mass, we get 38 here. So first observation is that we get state-of-the-art results, but those results are already very good just using text pretraining, and multimodal pretraining is only marginally better. Second conclusion is that text-only pretraining is much better than no pretraining. As you can see here, there's 3 to 4 improvement on the rule score. The third observation is that using the video is actually only marginally better, and not even always, than just using the ASR. So you can see here that we're about around 34 and 38 here with or without the video, which is kind of surprising because we would think that the video is important. But the speaker is quite descriptive in most of the videos, so this is understandable too. Our last conclusion is that the best model is close to human performance in all metrics here, except CIDR. So there's really a big gap in CIDR score. So maybe CIDR is the better score to look at in the future for those tasks. We have mostly focused on rule score because it is standard for summarization tasks. Here are the results on ViTT. We give those numbers mostly so that we can have a strong baseline on our new data set. We get the same conclusions as previously. We have also conducted an ablation study to better understand different effects. So the first thing is that we have compared 6-layer decoders versus 2-layer decoders. And you can see that using the 6-layer decoder is marginally better, but there's not much difference. And this is both with or without pre-training. The second observation is that, the second question is, could we use different video features? So we had used 2D features in the paper, but we also tried using S3D features, 3D, so 2-dimension space, 1-dimension time. And you can see they have very comparable scores. So we have just used 2D features for simplicity. Finally, we have compared bidirectional fine-tuning, so trying to also hallucinate the input from the output, against just unidirectional fine-tuning, the regular training objective. And we find that it helps mostly without pre-training. And our hypothesis is that it helps learn better word embeddings because those fine-tuning data sets are so small. It doesn't help much when we are doing pre-training. One important question that one can ask is, are the video features just too weak? Maybe the video features didn't help much because they were too weak. So to answer this question, we look at the validation scores for the pre-training tasks. And actually, they are quite high. On YouTube 8 million, we observed 90% accuracy on the alignment task and 80% on the ordering task. and lower but still quite high numbers for how to 100 million, 87% and 71.4%, whereas random guess would always yield 50%. So this suggests that our video features are reasonably strong and that the findings above are not due to weak visual representations. Conclusion. We have proposed a new dataset called video timeline tags, specifically for the task of timeline tagging. We have investigated many combinations of pre-training and fine-tuning objectives, yielding state-of-the-art on YouCook2 and strong baseline scores on ViTT. We get our best results using multimodal pretraining, but a significant gain is due to just using text-only mass. Though the video features are strong, we get good performance even without video. In the future, we will investigate end-to-end learning of video features, more pre-training objectives, ways to deal with optional inputs, and if there's a way to leverage on-screen text, since in a lot of the tutorials, the content creator will sometimes just write something on the screen but not say anything or show anything about it. That's all. Thank you.